Good evening, everyone. I hope you're doing well. And let's move on to our next lecture in the series of lectures on global climate change. Kind of picking up where we left off, we've talked about some of the basics of climate change. We've talked about some of the history of how climate change has been observed and how people, particularly the United States, but also globally, have responded to the observations about global climate change. But now let's take a look at the potential for there being other influences besides greenhouse gas emissions, besides fossil fuel combustion, for determining what might be driving the observed warming patterns that we're seeing today. We've already discussed just since the 1980s the observed pattern of warming. So keep in mind this is a science class, and so the idea that greenhouse gas emissions and their greenhouse effect, increasing the greenhouse effect, is what's driving this increasing temperature, that this is a hypothesis. And as a scientific hypothesis, the intent is to test it and reject it. And when you look at these numbers, starting in the late 1980s and continuing through to today, and keeping in mind that 2020, this year, is supposed to be, or at least it's on pace to be, the warmest year on record since 1880, it appears that none of the available data, none of what we see in this pattern of warming would be sufficient to reject the hypothesis. That being said, being good scientists, we're also supposed to look to see if there are other hypotheses, other potential explanations for what might be driving this warming. So, the point of this lecture will be to look at some of those alternative explanations for global warming, for global climate change, and see if we can't determine if there are any other more natural forces besides human activities that might be contributing to this warming. And so let's start off with where all our energy comes from, where the heat that is being trapped in the atmosphere comes from. Let's start with solar energy, because if the sun can be demonstrated to fluctuate in its energy output, and if those fluctuations correspond with what we're seeing in terms of global climate change here on Earth, then perhaps changing solar output, solar energy output, could explain the warming pattern we're seeing. And as it happens, the sun does go through cycles of increased solar radiation output and then reduced solar radiation output. So here you can see in this graph, you can see from the year 1985 through to today, to the year 2020. And you can see that here are three solar cycles, the most recent solar cycles that have been documented: cycle 22, 23, and 24. I'm probably not going to test you on that. But what I want you to see is when you reach the peak amount of energy, when these graphs are highest, versus when you hit the troughs, when the energy being released is at its least. And then we can cross-check this with what we've already documented, the warmest years on record. And so here you have 1987, 1988, excuse me, which is one of the warmest years on record in the 80s. Here you have 1995, 1997. And remember that whopping huge warm year, 1998? Well, here it is. And then you get into the 2000s, and there's 2005 and 2009. And then you get into the decade just passed. And there's 2016, which is currently the warmest year on record. And then 2020, the year we're in now, which again is on track to be the warmest year on record. And what you can clearly see here is that none of those peaks in Earth temperature correspond with peak energy output from the sun. And so, if you're going to argue that solar energy output is what is driving the warming, what you would expect to see is that as the sun is peaking out, as it's reaching its maximum solar output, that's when you would expect to see the warmest years here on the planet. Or you might argue, based on physics, and I'm not saying that you would argue this because I'm not a physics teacher. I am a part time instructor at a Cal State. But what you would expect, even if there was a lag built in, you would expect to see all of these arrows coming shortly either on the peak energy or perhaps shortly after the energy. That's not the pattern we see at all. We can see very clearly that what you're looking at is uh, almost all of these peaks coming at relatively low periods of solar output, which is not what you would expect if the sun was driving this. What's more, the pattern I just showed you is cycles 22, 23, and 24, but these cycles go back many decades. Obviously, here you can see from cycle 24 back to cycle 18, and you can probably imagine that the cycles go back all the way to cycle number 1. But if you're looking here just at this graph, you can see that, yes, what we're talking about is a pattern of about 10 or 11 years where the sun increases its solar energy output, it maximizes it, and then that drops back down, and then it increases and then reduces. And it's a fairly cyclical pattern, again, over about 10 or 11 years in cycles. And because this has been going on for so long and has been going on relatively consistently, whereas the warming that we are observing on the Earth is a relatively recent phenomenon, this would also argue that what we're looking at here is not driving the warming that we're seeing now. Now, as we talk about some of these different potential warming factors, I want you to keep in mind that changes in solar energy are contributing to changes in Earth's temperatures. The other factors that we're about to talk about are also contributing, but are they the main driving factor? Are they the chief explanation for why we are suddenly having short term dramatic warming over a period of just a few decades? So I don't want you to think that there's only one thing out of all the warming potential causes out there, that only one of them is actually doing any warming at all. There are plenty of reasons for Earth to be warm and to cool, and we're going to talk about them. But of all of the things that control or contribute to climate on planet Earth, which one of them is driving the current warming more than any others? And so looking at these data, you can see that it's probably not solar energy output, because the sun hasn't really changed its pattern of solar energy output over the past several decades. And that's why, if you take it back to the year 1880, you can see here you have, which is where our temperature chart earlier in the lecture and from last lecture comes from. You can see that solar irradiance is being traced in yellow across the bottom, whereas Earth temperature is being traced in red across the top. And they kind of sort of match each other up until about the year 1940, 1950. And then after that, solar irradiance starts to drop back down, whereas earthbound temperatures continue to really spike and take off to where we see them today. And so clearly there is a disconnect here. And so it's not the sun that is driving this, at least as far back as the year 1880. And we can even take it back further than that, because for scientists who study the sun, and you probably, if you've seen pictures of the sun, or maybe even looked at it during an eclipse, or even looked at it during a fire when you're looking at it through fire smoke, you can sometimes see these black splotches on the surface of the sun. And these are known as sunspots, very creatively named sunspots. And what happens is, with sunspots, when you have sunspots developing on the sun's surface, that means the sun is increasing the amount of energy that it is releasing. And so when you see those sunspots, it's kind of a proxy for whether energy is being released by the sun and how much energy is being released by the sun. If you examine the sun, please don't do this without the proper equipment, but when scientists who study the sun look at it and they see no sunspots on its surface, that means that it is producing relatively less solar energy. Whereas if you see a lot of sunspots on the surface, it's producing more solar energy. And this is important to keep in mind, because when you think about Galileo and other scientists of his time using telescopes to observe the stars and to observe the sun, and taking records of what they were observing. It means that going back not just a few decades back into the 1800s, but going back hundreds of years to the time of Galileo and other scientists of his time, we have physical records of sunspot activity on the surface of the sun. And It doesn't seem to make sense that a darkened spot on the surface of the sun would mean that there is more energy being released. But as it happens, when you find lots of sunspots, you have the darkened concentration on the surface of the sun. And around that sunspot, you have these very, very bright patches. These are called faculae. Faculae. You can see the word there on your screen. And faculae produce more energy than normal. And so, even though the sunspot itself means that in that concentrated area, there's a little less energy being released, the faculae around the sunspot are actually releasing more energy. And so, because of this, when you see sunspots, they are accompanied by faculae. And because the faculae release of energy overcomes and outweighs the reduction in energy from the sunspot itself, it means that you have more energy being produced. Write this down, it'll be on the test. You have more energy being produced by the sun during periods of high sunspot activity than you have during periods of low sunspot activity, which means if you go back to Galileo's records and records of other astronomers from that time, and you see renderings of the sun with lots of sunspots on them, you can determine that back then you were talking about a period of high solar energy output. And so the record that we see from historic times can be traced all the way back several hundred years, and we don't see a deviation in the pattern. We don't see anything out of whack with what the sun is doing now compared to what it's been doing for the past several hundred years. And that being the case, solar energy is not a good explanation for the current short term dramatic warming that we're seeing here on planet Earth. So we have to look for another potential excavation or explanation, excuse me. And so what about volcanic activity? What about volcanoes erupting and kicking greenhouse gases into the atmosphere that then can contribute to global warming? There have not been a lot of volcanic eruptions that have really caught the public eye. So, but nevertheless, it's something we would need to address. And as many of you may know, it was earlier this year that we celebrated the 40-year anniversary of the detonation of Mount St. Helens up in Washington. And Mount St. Helens exploded, and it blew huge amounts of ash and soot and smoke into the atmosphere. And it did change global weather, but it cooled it, because what happens is all of that ash and soot getting into the atmosphere blocks solar radiation from reaching the surface of the earth. And so there was a general overall net cooling effect down here in the troposphere. Now, all that material getting up into the atmosphere helped reflect more energy back into the stratosphere. And so in the stratosphere, there was actually a net heating, but down here in the troposphere, we're getting a net cooling effect. And so you don't see an increase in global climate change, global warming, based on volcanic activity. In fact, the United States Geological Survey has even said that the carbon dioxide released in contemporary volcanic eruptions has never caused detectable global warming of the atmosphere. All studies to date of global volcanic carbon dioxide emissions indicate that present day subaerial and submarine volcanoes release less than 1% of the carbon dioxide released currently by human activities. And so clearly, based on this, we can't argue that volcanic activity is contributing the greenhouse gases that are driving or interpreted to drive the current global warming, the global climate change phenomenon. What else can we look at? What other factors drive and contribute to global climate? Well, another one that does would be plate tectonics, where continents are located, how they move through time, and how they affect ocean currents and how they direct heat and cold currents. If you look at this map of global ocean currents, and remember our discussion of sea otters in Monterey Bay and how they live there and the kelp forests thrive there because of the cool California current. Well, if you look there over on the left of the United States, there's the cool California current labeled in blue. Where you see blue currents here, those are cooler currents. When you see red currents, those are warmer currents. Those are warmer water currents. And clearly, the positioning of the continents is what is determining where this coolness and where this warmth is being carried by the ocean. And I want to focus on that Gulf Stream current that you see there on to the right of the United States, because that is, geologically speaking, a relatively recent phenomenon. If you, I don't know if you knew this, but more than about 3 million years ago, North America and South America were not connected. And so the equatorial currents that flowed in that area flowed between the two continents before the isthmus formed between North and South America. And so you had a single tropical ocean with some water moving from the Pacific Ocean into the Atlantic and vice versa. Now, about 2.8 million years ago, the isthmus formed and that gap was closed. And suddenly, equatorial waters couldn't make it from the Pacific to the Atlantic or from the Atlantic to the Pacific. And so suddenly, all those equatorial warm waters in the Atlantic, unable to make it through into the Pacific, suddenly they're punted up northwards. And they're punted up north towards, away from North America and towards England and towards Europe. And so this is still going on today. This Gulf Stream is critical for controlling British and European temperatures in the old world today, which is why when you think about England, uh, its whole history has been based on having those warm ocean currents flowing past that island nation. And that's why, if you were to go to England and you wanted to look at, dinosaurs, because why wouldn't you? That's of course what you want to do. And this would be the Crystal Palace dinosaurs in England, outside of London. You could go there and look at them. And if you were at the same latitude looking at dinosaurs here in North America, say in Alberta, this is what you would see. It's a very different weather regime because you don't have that warm Gulf Stream keeping everything warm. And so ocean currents are particularly helpful for controlling and directing weather, and as a consequence, over the long term, determining climate. But please keep in mind, just as an example, that that Gulf Stream current has been active for over 2.5 million years. There haven't been any short-term dramatic changes in the positioning of the continents over the past few decades that would change ocean currents sufficiently so that they could change global climate. And so here again, you're not seeing anything with ocean currents driven by plate tectonics that could explain the warming patterns that we're seeing now. That's not the only way that plate tectonics can affect global climate. If you look at mountains that are built up through the activity of plate tectonics, like this one here, I'm sorry, that's the Expedition Everest ride at Walt Disney World. Let's look at the actual Mount Everest, which you see here. That's Mount Everest in the center of your screen. It is the tallest mountain on the planet, exclusive of volcanoes coming up from the ocean floor. What you might not know about Mount Everest is, even though it is the tallest peak on the planet, it is made of ocean rock. It is made of marine limestone. And here on the top of your screen, you see Mount Everest. And on the bottom of your screen, you see a geologic map of the different rock units that make up Mount Everest. And what's interesting, do you see those kind of pale yellow bands that are labeled YB? YB stands for yellow band, and it is a recognizable characteristic of Mount Everest and the surrounding mountains for those people who want to spend $60,000 or $80,000 and go climb Mount Everest. They recognize where they are in the mountain by the presence of that yellow band. That yellow band is made of marine limestone. It's made of ocean rock. It even has fossils in it, marine fossils in it. And I still think that's just one of the coolest geologic factors I've ever encountered, is that the tallest mountain on the planet is made of marine ocean rock from millions and millions of years ago. What happened is India used to be separate from Asia. It was termed the Indian subcontinent. And from about 70 million years ago up until the present day, that Indian subcontinent has been moving northwards relative to Asia and eventually impacted Asia and is still driving into Asia. It is still pile driving into Asia. And as it is hitting Asia, it is uplifting the Himalaya mountains. This is all plate tectonics. This is what plate tectonics does. You have the movement of a subcontinent into the much larger Eurasian plate, and where those two hit, that's where the Himalayas are uplifted. And that's how you get ocean rock that becomes the tallest mountain range on the planet. Why is this significant? What does it have to do with global climate change? Well, limestone reacts with the atmosphere because in the atmosphere, as we've already discussed, you have carbon dioxide. That is one of the major elements present in the atmosphere. But you also have water vapor. And water vapor and carbon dioxide will react with each other and combine with each other to form carbonic acid. And so this is why if you see older limestone buildings, if you go back east and you look at gravestones and you can see how they're weathered, it's because of carbonic acid. If you look at the pyramids or the Sphinx and you see how weathered it is, that is because of carbonic acid that is reacting with the limestone. Limestone and carbonic acid together produce calcium bicarbonate, which is an aqueous solution, and it binds with the carbon that is in the atmosphere and it traps it in that liquid. And then as the Sphinx wears down, as the pyramids wear down, as those gravestones you might see back east wear down, and as Mount Everest wears down, even as it's being uplifted, the erosion of that limestone takes carbon, takes that greenhouse gas out of the atmosphere and carries it away. So if you look at satellite images, this is all sediment. You can see this river draining here. This is coming off of the Himalayas. And you can see that all of that sediment is being carried away and buried in the Indian Ocean basin. And as it's being buried in the Indian Ocean basin, it is trapping or sequestering carbon with it that has been removed from the atmosphere. And what's interesting about that is that you can track that by looking through ancient temperatures and looking at how they change through time. From more than about 60 or 70 million years ago, you can see a global drop in temperature, which accompanies the uplifting of the Himalaya mountain range. And as it continues to erode, it continues to weather and wear and continues to trap and sequester carbon and remove it from the atmosphere. The uplift of those mountains over tens of millions of years has resulted in global cooling to where we are today. And so here's another way that plate tectonics can affect global climate. But number one, that is a cooling trend, so it doesn't match the warming pattern that we're seeing today. And number two, it takes place over tens of millions of years. The Himalaya mountains have not suddenly been reduced dramatically or uplifted dramatically just in the past few decades. So this is another very long-term, slow process that does contribute to global climate, but is not driving the warming that we are seeing today. Another way that plate tectonics has contributed to global climate is again with continental movement, where you have the continent of Antarctica ending up perched over the South Pole. It moved there, and that's where it is today. And because it is stationed there, that's why ice and snow can form so thickly on that continent. We don't have a continent, for example, in the Arctic on top of the North Pole. And so while you have sea ice there, it's not perched on dry land. And so it's more susceptible to melting than the ice and snow forming in Antarctica. So that drives climate down towards the south. But again, it's a long-term process. It is not a short-term thing. Antarctica didn't park over the South Pole just a few decades ago. So yes, this contributes to global climate. No, it is not responsible for driving the current warming patterns that we're seeing today. There are other features that take place, and we've talked about some of the weather patterns that go on. I mentioned this one briefly. This is what, if you look over here on the left-hand side of this diagram, you can probably figure out that that's Australia. And on the right-hand side, all those brown bits, that's North and part of South America. And what you're looking at is the Pacific Ocean. And in normal conditions, you have that red patch there. That is a patch of warm water. And because it's warm, there's evaporation there. And because of that evaporation, there is uplift and precipitation. We talked about this earlier in one of our lectures. And then there is convective circulation. It circles around towards the east, and then it drops back down as it cools over the United States, over North America, over Central and South America. And that is normal conditions. But as we mentioned last lecture, there is a phenomenon known as El Nino. And with El Nino, what you have is a much bigger warming patch in the middle of the Pacific Ocean. And so now the uplift, the high pressure area switches to the middle of the ocean, and you have two convective currents, one heading to the east, the other heading to the west. And this changes precipitation patterns, it changes ocean flow patterns. And as we mentioned last lecture, it can increase global temperatures in the short term. That's why 1998 was such an amazingly warm year. It's because on top of the natural, or the, excuse me, I almost said natural. It's not natural. On top of the observed global warming, there is the additional input from the El Nino event. And so this is a known factor. This can contribute to global warming, but usually it only lasts a year. It only happens once in a while. And sometimes we can even see it coming. And so since we are talking about consistent warming over the past 40 some odd years and more, this is not responsible for that either. It does occasionally contribute, as it did in 1998, but it's not a long-term contributor to global climate change. And finally, we can look at what the Earth itself is doing, and we can talk about movements of the Earth that are referred to as Milankovitch cycles. And they're named after this gentleman, Milutin Milankovitch, who's the person who worked them all out. And there's three different Milankovitch cycles that I want you to be responsible for. There's orbital eccentricity, there's axial tilt, and there's precession. And these three cycles account for most of the fluctuations in global climate that we see going back hundreds of thousands of years. So, for example, orbital eccentricity. We talked about this last time, where we talked, I think it was last time or the time before, where we talked about how the relationship of the Earth to the sun and the tilt of the Earth relative to the sun is what drives our seasons through the year. And as the Earth orbits the sun, we change our seasons. We're in fall right now, we're moving into winter, and then there will be spring and summer. And all of that is dependent in large part on where the Earth is in its orbit around the sun. But what's interesting is that the Earth's orbit is not a perfect circle because of other forces in the solar system, particularly the planet Jupiter. And I know if you were to look at it through binoculars or a telescope, it's just a bright dot in the sky, but it is actually an enormously massive planet. And even here, where we are in the solar system, the planet Earth can feel a gravitational tug from Jupiter. And because of that tug, our orbit is pulled a little bit out of true. And so there are times when Earth's orbit is more nearly circular around the sun, as you see here diagrammatically depicted on the left. And there are times when it is much more elliptical. And when it's elliptical, it means that during certain times of the year, we come much closer to the sun. And then later in the year, we're much further away from the sun. And so the change between more circular and more elliptical takes place over a period of around 100,000 years. And yes, this can drive climate change because this contributes to Earth's seasonality. And if you increase or decrease the length of seasons, you can affect climate here on Earth. But again, this is a long-term pattern, not nearly as long as the plate tectonics that we just talked about, anything like that, but still it is a 100,000-year cycle. It is not a short-term, decade-long cycle. So this is one cycle that does account for global climate change, but not the climate change, the warming that we are currently seeing. There's also axial tilt, also known as obliquity. And you're probably familiar with this, even if you aren't familiar with this, because at least if you've grown up in the United States and you have access to these things called globes, which practically every school had when I was a kid, at least, they're all tilted. You don't usually buy globes that are straight up and down. And that's because the Earth is actually tilted relative to the plane of the solar system. If you can imagine a horizontal plane running through the solar system, it's referred to as the ecliptic, and planet Earth is tilted relative to that ecliptic. And what that means is solar energy strikes the planet at different angles during different times of the year. We touched on this a couple of lectures ago. Again, this is what drives the seasons. Right now, we are moving in towards a season where North America is kind of facing away. It's angled more away from the sun, so the energy from the sun is reaching us more obliquely. That's why the sun is lower in the sky. By this time, not by this time, but by summer of next year, the sun will be much higher in the sky. That's because we have changed our position in orbit, and because of the Earth's tilt, the sun will be striking us much more directly, and you can hopefully see that depicted here. If we lived way up in the Yukon region there and northwards towards the North Pole, you can see that there are places where the sun never sets during the summertime in the northern hemisphere, whereas it would be the depths of winter in the southern hemisphere. Right now, we're on the other side of this. So we're getting to the point where if you lived up in the Yukon and points north, you would actually not see the sun. I was just up in the Yukon a couple of years ago, and the sun doesn't come up until about 10 in the morning, and then it hardly ascends in the sky at all, and then it drops right back down after a very short stint in the sky because they're so far north and because of how the Earth is tilted away from the sun. And so this also contributes to seasonality, but this tilt changes through time from about 22.1 degrees away from the ecliptic to about 24.5 degrees away from the ecliptic. So it becomes a little bit more oblique and then a little bit more acute over a period of about 40,000 years. And so here you have another of these Milankovitch cycles that is long term going to affect global climate and affect seasonality, but over 40,000 years. So it takes 40,000 years to go from 22.1 degrees down to 24.5 degrees and then back to 22.1 degrees. Right now, we're in about the middle of this. And so, yes, it is something that contributes to global climate and has and helps explain global climate observations going back hundreds of thousands of years, but it doesn't explain the warming that we're seeing now. The last of the Milankovitch cycles I want you to know would be precession, also known as wobble. And this is what the Earth does on its axis. It's not the axis changing its angle relative to the ecliptic. It's the axis wobbling a little bit. And the example that scientists usually like to use is if you have a top and you're spinning the top and it's spinning perfectly steady. As it starts to lose energy a little bit, it'll start to wobble, and the top of it will start to circle around in an ever increasing circle. That's what the Earth is doing on its axis now. And so this is another way that the Earth's relationship to the sun changes over a prolonged period of time, and that change will result in changes in Earth's climate over a prolonged period of time. In this case, we're talking about a cycle of about 26,000 years. And so keep in mind right now, if you're lost in the desert and it's nighttime, and if you're in the northern hemisphere and you know how to find the North Star, don't try that in 13,000 years, because 13,000 years from now, the Earth's axis will have wobbled away from the North Star, and the North Star there will actually be the star Vega in the constellation Lyra. And if you're looking at our current star, Polaris, it won't be north anymore because of this effect of precession, because of this wobbling of the Earth on its axis. And so 13,000 years from now, please don't use the same North Star that we're using today. Keep that in mind. Maybe write that one down. Good advice for your kids. Nevertheless, the point I want you to take home here is that this is another multi-thousand year cycle. It is not a short-term, decade-long cycle. And so if we look at the Milankovitch cycles, not a one of them is sufficient to explain the global warming that we're seeing now, the global climate change that we're observing now. So I've just given you pretty much all of the available possible causes of global climate change. And again, we're talking about global phenomena because that's what we are observing. We're not talking about snowstorms back east. We're not talking about droughts out west. We are talking about global patterns of warming. Yes, it manifests itself differently. And again, that will probably be a question on the final, but we're looking for global patterns. And we've talked about greenhouse gas emissions from fossil fuels. This explanation fits the data as carbon dioxide and methane and nitrous oxides and chlorofluorocarbons are pumped into the atmosphere through a variety of human activities. As they increase, global climate increases, and there seems to be a very tight correlation between those two. Milankovitch cycles, we just talked about, there is not a correlation. Those cycles take place over too long a time span to account for the warming we're seeing now. Solar energy output fluctuations also don't account for what we're seeing now because the solar output fluctuations have been consistent over the past several hundred years, and there's nothing unique about the current fluctuations that would suggest that there's been a change in solar energy output sufficient to explain the warming that we're currently seeing. Plate tectonics take place over millions of years. The volcanic eruptions that might result from plate tectonic forces are not sufficient to explain warming and, in fact, generally produce cooling. Same thing with volcanism. We don't see that. And finally, ocean currents have not changed sufficiently in the past few million years to account for the warming patterns that we're seeing now. And so this is hypothesis testing. And in the case of all but greenhouse gases, this is hypothesis rejecting. This is how science works. And so from a strictly scientific explanation, the only proposed explanation that matches the observed pattern of recent warming is that the warming is caused by greenhouse gas emissions from fossil fuel combustion. There are no other explanations available that will withstand scientific scrutiny and explain what we're seeing. I want to emphasize again that all of these other features are contributing. The Milankovitch cycles are still working, and that is having an effect. Solar energy output is having an effect. Plate tectonics continue to drive both volcanism and direct ocean currents, but all of these are normal contributors to climate, and they're not causing the spike that we're seeing. The only thing that is out of whack is the greenhouse gas emissions from fossil fuels. How bad is the warming? Well, you have to look at it historically. If we go back into prehistory and go back to the time of the dinosaurs, for example, you can look at the temperature of planet Earth over the past 500 million years. And here's where we are right now. That is the current warming. This is what we have been talking about so far during all of these global climate change lectures. And I want you to notice the little red dots over there on the right. You can see the one labeled 2050. That's where heating is expected to be unless something changes by the year 2050. And then above that, you can see the little red dot that's labeled 2100. That's where warming is expected to be, where it is projected to be without changing our actions by the year 2100. But compare that to some of the huge spikes in temperature over there on the left-hand side of this graph. For example, right here, that's an enormously warm temperature right there during the Cretaceous period, during the time of the last of the non-avian dinosaurs, the non-bird dinosaurs, the non-flying dinosaurs. And you can see that clearly that is much warmer than what we have today. And that's not even the warmest. Right here, between the Paleocene and the Eocene epochs, there's that little spike. It's called the PETM, and that's the Paleocene Eocene thermal maximum. That was a frighteningly hot period of time. I'm so glad I wasn't there, and there's probably any number of organisms that were alive at the time that wish they weren't there at that time. Very, very, very hot times during Earth's ancient history, and very clearly much warmer than what we see today. And so when we talk about warming today, This is not the warmest that it has been in Earth's history. It's not even close. I have mentioned that this is the warmest it's been in about the past 800,000 years. But if you go back millions of years, you can see that there are any number of periods that are far warmer than that. So, is this really all that bad? Well, I also want you to look at this graph and take a look at that right there over on the right. That is a relatively stable period of global climate going back over 11,000 years. And this period of time encompasses almost all of human history. In fact, it does encompass all of human history and a whole bunch of human prehistory as well. So when you look at that prolonged period of time, more than 10,000 years, all of the biological communities that we are familiar with today, that we interact with today, that we survive with today, and the biological processes that characterize them, they have all been enjoying a relatively stable climate for over 10,000 years. And so they've kind of settled into a routine, to use that's probably oversimplifying it, but go with it. They're doing this because they've been doing it successfully because that stable climate has enabled them to do that with minimum fluctuations. When you think about everything we talked about when we had our lecture on human populations, so much of what we talked about with Homo sapiens after about 20,000 years ago, expanding across the planet, moving into North America, developing agriculture, developing civilization, both in the old world and the new world, all of that was made possible because that agriculture and those civilizations were dependent on biological communities and biological processes that have remained stable because climate has remained stable for over 10,000 years. And so everything we are used to doing has a multi-thousand year background, a multi-thousand year, a 10,000 year and more history of consistency. And that's what, in part, has enabled these cultures to rise, agriculture to rise, and these civilizations to rise. And that is what is changing now. We haven't seen warming like this before. No humans have ever lived in times as warm as what we are currently experiencing in a global sense. You go back as far as 800,000 years ago, you're starting to get back in the Homo erectus range of early hominins, and yet we're not even back then they didn't see this level of warming. And so when you see this warming pattern, this is unique in the human experience. And this gets back to the previous lecture where I talked about earthquakes and how we see the results of earthquakes. And so we can viscerally appreciate that and respond to it. No humans in your going back over 10,000 years, no humans have seen the warming that we're seeing now. No humans have seen the effects of warming that we're seeing now. And it's not just humans, it's all of the other ecosystems, all of the other biological communities all across the planet that are also being exposed to these changing climates for the very first time. And so, with that, I'm going to end the lecture here. If you have any questions, once again, please feel free to reach out to me. In the interim, please keep yourselves safe, keep yourselves healthy. I hope you're all doing well, and please take care of yourselves. And we'll talk to you soon. Take care and have a good evening. Good night.